the effective action of a gauge theory of massless fermions, then if there is an anomaly, the covariant divergence of this variation will not vanish. This is the current, and the covariant divergence of that will not vanish. So let's define operators that are this with that. In other words, it's G mu with the variation of A. So this thing acts on functionals of A, first taking the functional derivative of A and then taking the covariant divergence of the answer. You can show that these things obey a Lie algebra. So, an anomaly, they'll be the same as the group that, of whatever the non-abelian group that A's are the gauge units on. Yeah. So, the anomaly is that equation. In fact, I don't want to waste valuable board space. So, under this way of looking at it, an anomaly is basically XA. Of course, these depend on X. Acting on gamma of A is going to be something non-zero, so let's call it G. And it will be a functional of the gauge field. So this isn't so far any big deal. It's just saying this covariant divergence isn't zero. Let's call it something, and let's call that something G. But now the commutators of these x's imply that XA commuted with GB of A is equal to F ABC GC of A delta of X minus Y, if that depends on X, and that depends on Y. Because it's a functional variation at A of X, this will give, this thing will be zero everywhere unless Y equals X, in which case we get a delta function. And this relationship is equivalent to saying delta U of G of VA, which I'll define in a minute, minus delta V acting on G of UA is equal to G of the commutator of UV with A. So what the heck do these things mean? Delta U is the integral of over X of UA XA. So I take this operator. Remember, this is a function of space-time points. So I integrate over space-time, and that's delta U, or delta V. And G of UA is defined to be the integral over X of UA GA of A of X. So if you integrate both sides, integrate over X times UA and over Y times GA, this relationship turns into that relationship. And so one can then ask, what is it that solves these equations? In other words, one can say this is what you get when you have an anomaly. And then one can ask what are the possible solutions to these equations. Maybe I should back up. It's not quite the anomaly yet. So what would be a solution? So let's take this, call it star. I think I'll just go here to rub off left. 5. So if I just look at it from a functional integral viewpoint, I have this functional g, and if there is an anomaly, then these x's can act on g like so, and can give me a set of equations. So I can ask, yes. D comma A, delta D, U comma A. Yeah, that's the functional argument where this thing here is that thing there, and so on. So it's like you smeared out G over some gauge parameter, and smeared out X over some other gauge parameters in space-time. That's basically what this is. The idea of this operation is to smear out over the delta function. So I've integrated times some gauge parameter over space-time for X, and likewise over G as well. So the question we can ask is, what are the solutions to star? Remember, G is a signature, there is an anomaly. If there's an anomaly, G will be 0. So one